Welcome back to part 2 of using first-order differential equations to model exponential growth. The differential equation dp dt equals k times p, or p prime of t equals k times p of t, is used to model exponential growth, which means the rate of growth is proportional to the population. Again, this is telling us the derivative of the function is equal to a constant times the function. And in part 1, we actually solved this differential equation and verified that the exponential function given below is the general solution to this differential equation. So now that we know this, we're going to use this exponential function to solve a second problem. A culture of bacteria grows proportional to its current population. Knowing this, we can use the model dp dt equals k times p of t, which we now know has a general solution of p of t equals p sub 0 times e raised to the power of kt. So if the initial population of 500 bacteria increases by 15% in 8 hours, what will the population be in 1 day? So the first thing we know is the initial population is 500, so p sub 0 equals 500. Next, the population increases by 15% in 8 hours, so that means p of 8 is going to be 500 plus an increase of 15%, so that would be 500 times 1.15. The 1 represents the initial 500, the 0.15 represents the increase of 15%. And this product is equal to 575. So P of 8 is equal to 575. Now we need to be careful because K is not equal to 15% because T represents the time in hours. So K represents the hourly growth rate, not the growth rate over 8 hours. So what we're going to do now is use this information to find the hourly growth rate, and then we can answer the question of what the population will be in 1 day, which is equal to 24 hours. So again, using the exponential function p of t equals p sub 0 times e raised to the power of kt, we know after 8 hours the population is 575. We know the initial population, p sub 0, is 500, times e raised to the power of k, which we don't know, and t is the time, which to increase to 575 is 8 hours, so our exponent is 8k. Now we'll isolate e by dividing both sides by 500. This is 1, so we have 575 divided by 500 must equal e raised to the power of 8k. And now we can take the natural log of both sides of the equation and apply the power property of logarithms. So now we can move this exponent here to the front. This quotient here is just 1.15. And on the right side we have 8k times natural log e, but natural log e is equal to 1. So now we just divide both sides by 8. This will give us our growth rate. We'll go ahead and use the first 5 decimal places, so the growth rate is 0.01747. Which means for this situation the function would be p of t equals 500 times e raised to the power of 0.01747 times t, where t is the time in hours. So now that we have this, we can determine what the population would be after 1 day or 24 hours. Let's do that on the next slide. So p of 24 is going to be equal to 500 times e raised to the power of 0.01747 times 24. And we'll go back to the calculator one more time. 500 times e raised to the power of 0.01747 times 24. And so there will be approximately 760 bacteria after 24 hours or 1 day. Okay, next we'll take a look at exponential decay. I hope you found this helpful.